Well, this is electric circuits course of second semester students in the Department of Electrical Engineering, UET Lahore, and I am Dr. Khalid Ahmad. This is our textbook, and in this lecture we'll discuss chapter number 5 of the textbook, which is on signal waveforms, and this is part 1 of the lecture. What is a signal? Signal is a detectable physical quantity, and in electrical engineering uh, we consider current and voltage. This representation shows the variation in current with respect to time and variation of voltage with respect to time. You will see that in some texts only lowercase letter I and V are used to represent the variation in voltage and in current, and sometimes we show it explicitly Vt and It, where T is independent variable. A waveform is the graph that defines the signal as a function of time. For example, if this is a voltage, which is sinusoidal voltage with respect to time seconds, and this is T with some defined amplitude and the time period over here. It may be a constant quantity, means the voltage Vt, it remains fixed, say at 10 volt level for all the time. Waveforms of few basic signals used in this course and generally in electrical engineering. This is step waveform, and in the step waveform, if the amplitude is 1, then this is known as unit step signal, unit step function or signal. And sorry for this. I wanted to use this. So if the amplitude is 1, it is unit step. And this is a sinusoidal waveform. You all know that, the sinusoidal waveform. And in the sinusoidal waveform, this part of the waveform is repeated again and again, and time spent in one revolution or in one cycle is known as time period, and its amplitude, say this is Va. And next one is a pulse train. We have pulses of short duration and again pulses of short duration. The next signal is a square waveform. The amplitude, the positive and negative side, is not mentioned. This is exponential signal, and this exponential function, this is decaying exponential with negative sign. This is T divided by T, say Tc, where Tc is constant. We'll call it time constant. So remember, if it is negative, if the sign of the power of exponential function is negative, then it will be exponentially decaying. And you can say that what is this signal in the negative side, means when when time is negative, when time is less than 0. So if we extend it, it will be like this. But you will see later that we consider the waveform after t equal to 0. After t equal to 0, we'll consider it over here. But if we take it, if we draw minus t over tc, its waveform will be like this. When t is equal to 0 second, this is equal to 1, and for negative and positive, it will be like this. So I'm just sketching it over here. Then damped sinusoid, basically here we have a sinusoid, over here we have a sinusoid of fixed amplitude, the positive and negative side fixed, and multiplied by a decaying exponential signal over here like this. So when we multiply these two, we have damped sinusoid. Then sawtooth waveform and triangular waveform. Now I will introduce a few basic signals. So in this is a signal or function, step function. Step function, the waveform of step function is like this. This is t and seconds and say voltage. So step voltage can be shown like this. This is the step voltage. What does it mean? If its amplitude is VA, what does it mean? It means that we have a voltage source, DC voltage source, and we have a switch over here with two positions. So this is the switch on. So this is off position and this is on position. And here we have some circuit, and just two terminals, two input circuit, and the voltage over here. What is the voltage? So say VT. So when the switch is in off position, VT is equal to 0. You know, this negative side connected to ground and the positive side over here connected to ground. Therefore, the VT is equal to 0. When the switch is in on position, means the switch is this switch is now here. So what is the voltage? Positive side is connected to this positive side of the voltage source, and the negative side it is connected to the ground, and VA source is also connected to ground. Then therefore this VT is equal to VA. Now usually you will see a switch with an arrow, and this arrow tells us the time at which the switch position is changed from off to on. Look at the arrow. The switch arm is moved from off position to on position at t equal to 0. Now how we express this unit step function mathematically. So this unit step function, this is 0 for t less than 0. Look at here, t less than 0, we have a reference 0 over here, this is 0, and this is equal to 1 for t greater than or equal to 0. So this part is 1. 1, if it is a unit step function, its amplitude is 1. Now if it is VA, we can write it as VA ut. It means that it is 0 for t less than 0 and VA for t greater than or equal to 0. Now the whole mechanism over here, encircled mechanism, the whole mechanism can be shown like this: VA ut. This VA due to this voltage and ut due to the switch. The switch position is moved from off to on at t equal to 0. Now, as you know, in the circuit analysis, we express our circuit in mathematical equations. Therefore, if we express the input to the circuit like VA ut, so this is the mathematical representation. This is the mathematical representation of whatever we see over here with the switch mechanism. Either we have to show the switch or we write VA ut, both have same meaning. Now this VA ut, we will be using this VA ut in the following discussion in circuit analysis, just to show as if we have a switch which is moved from off position to on position at t equal to 0. Now there are few important things associated with the step function, and this is a time shift. This time shift means if we have, this is t and seconds over here and this is Vt, it is important to show the units. V means volts, it may be millivolt, microvolt or kilovolt. It is important to show time, units of time. It may be microsecond, millisecond or seconds. It may be hour, but we have to show it, the time, unit of time. This is the origin, and the unit step function defined with the help of this equation can be shown like this. For t less than 0, it is 0, and for t equal to 0, equal to and greater than 0, it is 1, and we use a vertical line to join this. So this is ut. Now interesting feature with the time shift you will see over here is that if we have a unit step, again I will reproduce this. Now I will shift the origin to, if I shift this origin to negative side by an amount t, This is any fixed time, 1 second, 2 second, 1 millisecond, microsecond, 1 hour, whatever it may be. Now if I shift the origin, which is the origin over here, which is the origin, if I shift the origin to the left hand side, to the negative side, means this is, I am discarding this origin and new origin is over here. Then the same unit step, which is unit step, will be represented by ut minus t. As we have this negative sign, means we have shifted the origin to negative side by an amount t. This is very important, and I'll show you few more examples of this. If I have this unit step function and here, and I shift the origin, now I will shift this origin to positive side, say over here. Now it is sorry, it is the vertical line is going with it, so it is I will redraw it over here, and it was this. So what I have done, originally this was the origin and I have shifted it towards right hand side by an amount t. This is fixed time. Then the representation of this time shifted unit step function will be ut, to which direction I have shifted the origin, to positive side. So I will discard this 0 and this is our new 0 with this shift, because it is shifted to positive side by an amount t. So this is ut plus t. Now with this time shift we can generate very interesting waveforms. Again, if we have a unit step function, I will draw two unit step function and say this is ut, as our origin is here, and again I will say this is again ut. So both are unit step function without any shift. Now in it, if we shift the origin, this origin, to negative side, and this shift is over here t seconds, it means that our new origin is over here and we discard the previous origin. As we are considering unit step, therefore its amplitude is 1. Now we align these two functions such that its their origin is aligned, and this is Vt volts and this is again Vt volts, unit is volt, and this is second. This is important, don't forget this. Now consider this is a waveform and this is B waveform. So what is A minus B? Let us redraw what is A minus B. So t seconds and V3 volt. So A minus B, from minus infinity to 0, signal the waveform A is 0, from minus infinity to 0, waveform B is 0, therefore A minus B is 0 as well. Now, from 0 to t seconds, the B waveform is 0. From 0 to t seconds, the A waveform is 1. Therefore, A minus B is 1. So, if we consider this over here, so A minus B is 1. Then, from this time instant to positive sides towards positive infinity, the B signal is 1, and from this time instant, the same time instant towards positive infinity, A waveform is 1. So 1 minus 1 is equal to 0. Therefore, this is 0. It means that if we represent the voltage over here, this voltage over here, this is ut. Sorry, I forgot to show it over here. This is, we have shifted the origin to negative side. So this is ut minus ut minus t. So it is this waveform. And if this waveform, this is the Vt applied to a circuit over here with the reference polarity. This is a circuit we want to analyze, and this circuit is represented in the form of mathematical equations. The input must be expressed in the form of a mathematical expression, which is over here ut minus t. It also, if we show it graphically, it means that we have a voltage source, as if we have a voltage source, say of 1 volt, and there is a switch, and the switch arm is shown over here. This is the switch arm. This is at position 1, this is position 2. So this switch arm is at position 1 from minus infinity to t equal to 0, and at t equal to 0 it is moved to this position. At t equal to 0 it is moved to position B. Therefore, the voltage over here is 1 volt, as it is moved to the position B. When it is moved to position B, in position 1, when the switch is in position 1, the voltage VA is 0, and this 0 is shown over here, 0. So at t equal to 0, the switch is moved to position 2. I will show it here. The switch is moved to position 2. Now in this position, you will see that VA, this voltage is equal to 1 volt. Whatever is the voltage over here, whatever the voltage. Now again, at t equal to t seconds, we move the switch from position 2 to position 1 again, and in this position this VA is again 0, so this is 0. So the whole mechanism over here, the encircled mechanism over here, the whole mechanism can be shown as, in the mathematical expression, it is ut minus t. We may have a circuit which requires, say, 10 volts for initial 5 seconds. Note that this 0 is a reference time. Reference time means time at which we start analyzing our circuit. So for 5 seconds, say I'll again draw a circuit over here. This is a circuit, and the voltage over here, the voltage here is 10 volt. Then at 5 seconds, the voltage, the input voltage, it is our requirement that the input voltage should be minus 5 seconds, and this voltage minus 5 seconds, and this voltage should be there at the input minus 5, means the voltage here is now with this polarity. Minus 5 volt means, so in the initial part it is 10 volt, and then it is minus, plus, and 5 volt. So it means that voltage is minus 5 volt, and with this polarity it means that voltage is 10 volt. And I will leave it to the original position. This is the voltage over here. Now after 10, if we assume that after 10 seconds the voltage should be 0, so basically we can do this with the help of two sources. Say this is 10 volt, and this is 5 volt source, and say we have this is connected to ground, and we have a terminal over here connected to ground, and we have this is also connected to ground, and I will try to show you a switch. So say the switch is over here. Initially it is at position 1. Say this is this time. It has been in position 1. Then the switch is moved to position 2. When the switch is moved to position 2, then the voltage over here, this voltage is 10 volt, and then the switch is moved to, at 5 seconds, the switch is moved to this position, position 3, to this position. And what is the voltage to the circuit? It is minus 5 volt. Sorry, the polarity, it should be minus and plus. This is minus 5 volt is the polarity of the voltage. I mean this voltage, because one side is connected to ground and the other side is connected to the negative side of a voltage source. It is minus 5 volt is the voltage input to the circuit. And then at 10 seconds, when time reaches 10 seconds, the switch is moved to, this switch is moved to position 4. This is position 4, and due to this position, the positive side is again connected to the ground, and while the negative side is also connected to the ground, therefore the voltage is 0. So instead of showing this complex diagram, we just write Vt here, and then we try to express this in the form of mathematical equation. So what it should be, how we can represent this waveform mathematically. How we can do this? This is for beginners, it may be it may not be very straightforward. So I will show you step-by-step procedure. So consider a unit step function, and if I consider the unit step function, this Vt, this is ut, but we need amplitude of 10, therefore I write 10 over here. So this is the waveform of this signal 10 function 10 ut. Now if I have another step function, this is 5 corresponding to this, and this time is 10 seconds corresponding to that. Now consider another step function which is like this at 5, and I'll show it in green color. This is 5 and this is minus 15. Now this signal is basically derived from a unit step, as its amplitude is 15 but with negative sign, and the origin is shifted to the negative side. Look at this, the origin was here and it is shifted to negative side by an amount 5 seconds. So I will show it t minus 5 over here. And I will write it as minus 15 ut minus 5. So let us decide about the result of these two. From minus infinity to 0, remember this is the origin, both signals, this is 0 and this is also 0, and our resultant, I will show the resultant over here t seconds, and this is Vt. From minus infinity to this origin, both are 0, therefore we have 0. Then from 0 to 5 seconds, this signal is 0 and this signal is 10 ut is 10. So what is 10 ut minus 15t minus 5? This is equal to 10. This is equal to 10. Remember again, see again, this signal is waveform is 10 and the green was 0, so 10 minus 0 is 10, as you can see over here. It's very straightforward. Then from the time equal to 5 seconds and onward, ut is 10 ut is 10, and the other signal which is over here, this is minus 15. So what is the result of this operation? We are subtracting one signal from the other. So this is amplitude is 10 and this is minus 15. So it is clear that 10 minus 15 is minus 5. So this is minus 5. This is minus 5. But look at the original waveform, which is the required waveform. The original waveform is shown over there. Perhaps it is due to, not sure, sorry, I wanted to remove this. There's some problem in my light pen. I don't know why it is not working over here. So let us keep it over here. It's, I was discussing this. So what we have done, look at this figure, this waveform. This part is same, and then this part is same, but we need -5 volt up to 10 seconds. Up to 10 seconds. Say this is 10 seconds. This is 10 seconds. Now, if we have another signal, of 5 ut minus 10, so what is the waveform of this signal? Say this is 5 and this is 10, origin. Basic step function is this, amplitude 5, so this is 5 ut. But if we shift the origin towards negative side, this is -5 and this is -10. If we shift the origin, we are shifting this origin towards negative side, shift it here. Then the same signal, which is now shifted, will be represented by t minus 10, as it has been shifted towards negative side by an amount 10 seconds. Shifted towards negative side by an amount 10 seconds. Remember, if I show this signal on this waveform, just in a dashed form like this, and this signal is 5 ut minus 10, this signal, which is this. Then we will see that from 10 to onward it is -5, and this signal from 10 to onward is +5. Therefore, our resultant signal, it becomes 10 volt from 0 to 5, -5 volt from 5 to 10 seconds, and then 0 volt from 10 to onward. And there are many other examples in the textbook. You can see there is another interesting function which we will derive from the step function. This is t in seconds, and say this is voltage, and if we have this waveform, and say this is t by 2 and minus t by 2, and due to some reasons we would like to keep the area. If we want to keep the area of this waveform equal to unity, then what is the width? This width is t by 2 plus t by 2 is t. So if we want area of 1 means unity, so what should be its height? Its height should be 1 divided by t, means this point. Now, if we reduce the width to t by 4 and t by 4, it means that this is then the width is then t by 4 plus t by 4 is t by 2. What should be height such that the area should be 1? Then this should be 2 divided by t, means its height. Look at the waveform. So this should be 2 by t. Now if we keep on reducing the width, say this time this width is t by 10 and t by 10. So what is this width? T by 10 plus t by 10, t by 5. And what should be the area? Area should be 1. In order to keep the area 1, the height of this should be 5 divided by t. So it means that if we keep on reducing the width, the height will be increasing. If we keep on reducing the width, the height will be increasing. This is not a very good sketch over here, so you can follow the textbook. So it means that reducing the width over here, for this width, this is the height, and for this width, this is the height, and again for this width the height is. So as the width over here, as the width approaches to 0, the height approaches infinity. And we can then show this as should be a vertical line like this, and over here t second, and v t in volts, and it can be shown as just a single line over here and approaching to infinity. So now, due to reasons, we use a unit impulse function. You will see the detailed mathematical description due to limits in another course in higher level, in higher semesters. The course is Signals and Systems, and the unit step function represented by delta, it is function of time. We call it 0 for t less than 0. Let us sketch its waveform. T seconds, and say it is voltage. So and our origin is 0 over here. T less than 0 is shown in yellow, it is 0. It is also 0 for t greater than 0. This is very interesting. For t greater than 0, it is also 0. But there is a time when t is equal to 0, and this is the instant of time t is equal to 0, and at this instant of time, this is undefined. This is undefined. This is the original impulse function. And unit impulse function is in the unit impulse function, this undefined will be defined value which is equal to 1 when t is equal to 0, and we show the amplitude 1 over here. We show the amplitude 1 over here. It is just like a shock to a circuit. Say for example, this is a circuit and we want to see the response of a circuit. If we apply some voltage to this suddenly, if we apply this suddenly, say for example we have a switch which is on when it is pressed, and we press it for very short time. Practically, if we want to implement this waveform practically, it is very difficult. Practically, if we press the switch, which I have shown over here, if we press the switch and our reference time is 0, then the shape may be considered as, if we want to press the switch, it may be like this, so over here like this, or in higher level courses you will also see a waveform like this, with this over here. But the mathematical representation of this waveform is complicated, therefore we don't use this in this course at least, and we consider a voltage of amplitude 1 when t is equal to 0. Another thing which is associated with this impulse function is the strength of the impulse. Means strength of impulse function if it is simply delta t, its strength is 1. If it is say 2 delta t, its strength is 2. If it is 10, its strength is 10. It may be several kilovolts, say 10 kilovolts, say 10 kilovolts, so it is 10 kilovolts. So we use this high voltage impulse to test a circuit, usually for its insulation. There is a time shift associated with this impulse function as well. Now I'll show you what is delta t, what is delta t minus t, and what is delta t plus t. I will consider unit impulse for simplicity, t in seconds, and t in seconds. This is in volts. So origin is here, and this is the unit impulse function. And delta t minus t means origin is shifted towards negative side. It means that if this is t, then delta t minus t should be represented by this. This is 1. Note that originally it was in delta, it was here. This is delta t only, and if we shift it to an amount t seconds towards negative side, it becomes delta t minus t. Again, if the original unit impulse is this and we shift the origin towards positive side by an amount t second, what it should be then, so I am shifting this origin to here, it's going with that, sorry, it should not be like this, I will redraw it. It is over here, and if I shift it to positive side by an amount t seconds, it will be like this. So I will just select this to positive side by an amount t. So it will be this, and now our origin will be this. This will be our origin. So this is t plus t. We have shifted the origin to positive side. The 0 should not be over here. And delta t minus t, we have shifted the origin to the negative side. This is the original impulse function without any shift. Another interesting feature of this unit impulse function is that I'll show you only a brief introduction. This is say time axis, and this is say voltage and V. What is this? This is delta t, and if this is say t second, and this is 2t second and 3t second and 4t and 5t and so on and so forth. What will be this? What will be this? Only this. This will be delta t minus t, because we are shifting the origin to the negative side. I will repeat. If we have over here, if this is the origin, this is the original unit step function, and now if I shift the origin to negative sides, this I don't know why it is copied over here, it should remain here. So as our origin was here and we have shifted the origin to this side, to the negative side, this is delta t minus t, because we have said that this shift is t seconds. So this is delta t minus t. Likewise, only this means if we see only this impulse over here at 2t, this will be known as delta t minus 2t. And now if we see an impulse here at 3t, this will be represented as delta t minus 3t. Again, I will repeat, origin was here and we have shifted the origin to negative side by an amount 3t seconds. Now we represent it again here. This is delta t minus 3t. Now this is a train of impulses, and this train of impulses is used extensively in electrical engineering. And this voltage, we will see the voltage. This is this delta T plus delta T minus T plus delta T minus 2T plus delta T minus 3T, and so on and so forth. So this is a train of impulses, and this train of impulses, this concept is extensively used in digital signal processing. You will study in the following semesters. The third signal, the third function is a ramp function or unit ramp function. Due to the name we are using, this is T and second, say we are considering it as a voltage, means we can think of a circuit, and a mechanism may be like this, which is okay, I'll show it with a switch mechanism, which is here, and this is a voltage source, say this is VA, and I will use a variable voltage symbol over here. And if we assume that the switch has been in this position from minus infinity to t equal to 0, we use t equal to 0 as our reference time of analysis, and then we move this switch to position 2 at t equal to 0. So we draw the waveform, and in it, as long as the switch is in this position, it is we can show it as 0 volt, so this voltage will be 0. But when the switch is moved to position 2, when the switch is moved to position 2, this is position 1, and now the switch is moved to position 2 at t equal to 0, at t equal to 0. Then if initially this voltage is 0, this is the variable voltage, and then we keep on increasing the voltage. If we keep on increasing the voltage at constant slope like this, it means that we are increasing the voltage. And what is the rate of this increment of this voltage? Say this is 1 second and 2 second and 3 second. So if at 0 seconds it is 0 volt, and 1 second it is 1 volt, and at 2 seconds it is 2 volt, and at 3 seconds this is equal to 3, then its waveform will be like this. Now the ramp signal, the definition of mathematical definition of a ramp signal, we use the letter R to represent it. So the ramp signal, it is 0 for t less than or equal to 0, and it is equal to t when t is greater than or equal to 0. This is a unit ramp signal. Unit ramp signal means it is t. So if we draw again, if this is t, and if we draw a voltage which is equal to t, it will be like this. So say for 10 seconds this will be 10 volts. So its slope is 1, its slope is unity. So if the slope is unity, it is known as unit ramp signal, unit ramp signal. Otherwise, we can show the slope over here. We can show the slope, say this is say ART, we can show it over here, AT. Now we have time shifted ramp signal or ramp function. So we have seen what is RT. RT is like this, T seconds. We will, instead of writing again and again second, we will assume that T is in seconds. So this is unit ramp signal. Say this is 1 and this is equal to 1. Now if we have this unit ramp, its shape will be like this, and again say this is 1, its value at 1 second is 1. Now if we shift the origin, if we shift, this is the origin, and if we shift this origin to negative side by an amount T seconds, then this will be represented as RT minus T. We have shifted the origin to the negative side. Similarly, we have a unit ramp signal over here, and say this is -1 and this is 1 on the time axis in seconds. Now if we shift this origin to positive side by an amount T, and in this case T is 1 second, then this will be represented as T plus T, as we have shifted the origin to positive side. Remember, as we have shifted the origin to positive side. So with these operations we can generate various types of waveforms. Those simple types of waveforms we can generate with these operations. Say for example, we need this is T, and in seconds we need a voltage as an input voltage to a circuit. Say this is 1 second and this is 10. Then this is how we can represent the voltage, how we can represent this waveform mathematically. It can be done we can use various methods to represent this waveform. I will discuss only one method. So again, it is if I consider a ramp signal is a ramp signal such that at 1 second this is equal to 10. This is due to our requirement that we need this type of voltage, at the input of some circuit we are analyzing. Then first thing we can take is this is 10 RT, which is this signal. Now if we consider another function as this is 1. So just consider this function. This is 1. So what is this function? We have seen previously that this is ut minus 1. Now if we multiply these two functions, means if we multiply 10 RT and ut minus t, what will be the result? We can see over here t, and the results of multiplying these two from minus infinity to 0, it is 0 multiplied by 0, and this is 0 over here. Now from t equal to 0 to 1 second, this is 1, and from t from 0 to 1, this is a ramp signal with a slope of 10. Therefore the product is shown over here. This product is shown like this, and this is equal to 10. What will be after that? After that, when t is greater than 1 on this side, this is 10 RT, but the other signal over here, this is 0. Therefore the product will be 0. But look at the original requirement. In our original requirement, the voltage should be 0, and then from t 0 to 1 second it should have a slope of 10, and from t equal to 1 second and onward the voltage should be 10 volts. This is according to our requirement. This fulfills our requirement, but this part, it does not fulfill our requirement. Then what to do then? So one thing which we can do is that, as I told you, there are more than one methods to represent the required signal. Just assume that we have another function which is say its amplitude is 10. What is this function. This is 10 ut minus 1, because originally the origin was here and we have shifted the origin to the negative side over here, remember. Therefore, it is ut minus 1, 10 ut minus 1. Now, add these two. What I am saying, initially we have this, and now what we are doing? We are adding, this is 10, we are subtracting, we are then subtracting minus 10 ut minus 1. Sorry for confusion, in fact we are adding. So if we add these two signals, over here, t, and this is 1 second, so adding these two, adding this and this, so from minus infinity to 0, this is 0, this is 0, and this is also 0. And from t equal to 0 to 1, this is a line with the slope 10, and this is 0. So therefore, we have the same thing, and this is equal to 10. And after that, when t is greater than 1, this is 0 and this is 10. Therefore, we have 10 over here. So this signal, this over here, can be shown like this. So basically we have this plus this. So we have yet another representation of the same thing, the same signal, and I will advise you to see the text. There are many examples in it. In the textbook there is another example, and in this example we need a voltage of the waveform shown over here. So first of all 1 and 2 and 3, 4, 5, and the voltage unit is a volt, and we need a voltage waveform like this. At the input of some circuit, and this is 2, and the value over here, this is 4, and at 3 seconds this is equal to 6 volts. So how we can generate this waveform? With the help of ramp signals, shifted ramp signals, unit step, and shifted unit step functions. Now let us consider here t and seconds. So let us consider a ramp function like this, and reference values are produced over here, 1, 2 and 3, and this is 2, this is 4, and this is 6. So you can see that This red waveform is, what is the slope? Slope is 2. And if we represent it, if we say it is 2t, and this 2t means it is this 2t, we should remember, from minus infinity to t equal to 0, or when t is less than 0, this is 0, and when t is greater than or equal to 0, this is 2t. And we can say that this is a ramp signal of slope 2, ramp signal, and this is, because we define the ramp signal, we have defined the ramp signal over here, that it is 0 for t less than or equal to 0, and this is equal to at, whatever is the slope a. So the slope over here, the slope which we see over here, our slope is 2, therefore it is 2 RT. We can consider another waveform, again reference, these are the axis on the values on the t-axis. If we consider a waveform like this, so what will be this waveform? While our origin is over here, this waveform is derived from unit step function ut minus 1 due to this, if its amplitude is 1, and there is another, there is a minus ut minus 3. What I am saying? I am saying that t and of course in seconds, and if I have a step function and another step function, this step function is ut minus 1 because the origin is shifted to negative side, and this is ut minus 3, this is 3 seconds because origin has been shifted to negative side by an amount 3 seconds. Now due to these two, if we see what is ut minus 1 minus ut minus 3 means if it is a and b, so what is this? This is a minus b. So you see from minus infinity to 1 second, a is 0, and from minus infinity to 1 second, b is also 0, therefore the difference is 0. And then from 1 second to onward, a is 1, and from 1 second to onward, b is 0, therefore a minus b is 1. Then for t equal to or greater than 3, a is 1 and b is also 1, 1 minus 1 is 0. So we have this signal. So I will delete everything, and then you can always see its recording again and again. We call this signal, the signal shown over here, we call this signal as a gating signal, this signal as gating signal or gating function, because Uh, if we consider it A and we consider it B and we multiply A and B, what we'll be getting? T. So look at A. From minus infinity to 0, A is 0, B is also 0, therefore this is 0. A multiplied by B is 0. Then what is A from 0 to 1 second? It's the ramp with the slope 2. What is B from 0 to 1 second? It is 0. Therefore, the product is also 0. Then what is A from t equal to 1 and 1 to 3? This is this part of the ramp signal. And what is B? This is 1. From 0 to 3 seconds, this is 1. So multiply these two. We will have the value over here is 2, and this is 1, and we will have 2 over here. This value is 2. I'll show it in red. So at 3 seconds, this is 6, and this is 1, so it will be 6. And after that, from 3 to onward, A waveform is a ramp with a slope 2 and B waveform is 0. Therefore, the product will be like this. So, what you can do over here? We can express the waveform as say 2R T multiplied by this. So this is ut minus 1 minus ut minus 3. This RT, you can show it as a T, 2T, ut minus 1 minus ut minus 3. And then we can further manipulate it. This is 2T ut minus 1 minus 2T ut minus 3. We multiply it inside. And then we do a little manipulation to this T over here. We show it like T minus 1 plus 1. Multiplied by ut minus 1 minus, and this T, we show this T as T minus 3 plus 3 multiplied by ut minus 3. There is 2 over here. Now this 2 is reproduced over here 2, and this T minus 1 part with this ut minus 1. So this is T minus 1 and ut minus 1, and then this plus 1 multiplied by ut. So we write it as plus 2 ut minus 1, and then this part, it is minus 2 T minus 3 multiplied by ut minus 3, and then this part plus 3, because 2 is also multiplied, so this is equal to minus 6. 2 is multiplied by 3, 2 multiplied by 3, and this is ut minus 3. Now we see what is this signal. What is this? We can represent it as 2RT minus 1, then this as such plus 2UT minus 1. Then what is this? This is minus 2RT minus 3, and the last one minus 6UT minus 3. So this is another representation of the same signal. You may practice it by yourself in order to understand it fully. It's not difficult, it's easy. The last thing over here, this voltage can be defined as, this is 0 for t less than 1, this is 2t for t greater than 1 and less than 3, and 0 again for t greater than 3. So if this type of voltage is required, the mathematical description over here will be like this, and in the form of function it is over here. We may have a circuit, over here, and we need a voltage of this form to be applied over here in order to test the circuit. So the circuit will be represented in the form of equations, and the input over here. So we should have a mathematical representation of the input voltage in order to analyze the circuit. So this is end of part 1. And in part 2, I will discuss exponential waveform. Exponential waveforms are exponential function